So it is a really nice way of identifying, okay, is it better if I invest money in decreasing my car weight by 50 kilos, or should I increase my power by 5%? You can actually simulate that in Optimum Lab with minimal inputs, and you're going to get a very accurate answer.
Welcome to the HPA Tuned In podcast. I'm Andre, your host, and in this episode, we're joined by Bruno from Optimum G. Now, Optimum G is a name that I've been aware of basically since I got involved in the automotive industry. If you haven't heard of the name, you'll find out exactly what they do as we get into our interview, but essentially they offer software packages for analyzing and optimizing all facets of race car performance. They also do consulting work for OE manufacturers as well as high-end race teams, and they run training seminars. Now, from the outside, I'd always assumed that essentially you'd need a PhD in order to be able to use the software products that Optimum G provide, or alternatively get involved in one of their seminars. While their topic content is quite deep, and vehicle dynamics is a complex topic in and of itself, you'll find out as we go through this interview with Bruno that no, you absolutely do not need a PhD. Really interesting on this topic as well, because prior to reaching out to Bruno and getting him on this podcast, we actually had the opportunity to use some of Optimum G's software packages around the development of the suspension on our Honda CRX. And while initially it looks complex, it's actually not very difficult to use, and once we dived into it, it is incredibly powerful. This is a really deep dive into the world of vehicle dynamics, suspension kinematics, and all of this really is just about optimizing the tire contact patch with the racetrack surface. Obviously, no matter what car we've got, how much power it's got, how much money has been poured into developing it, ultimately, the performance of every car is limited to that tire contact patch, so we absolutely want to make the most of it. I also used this as an opportunity to really pick Bruno's brains for my own benefit, and hopefully everyone listening is also going to benefit from that discussion as well. We get deep in the weeds in this conversation with some of the less obvious or less well-known terms around suspension design and suspension kinematics, such as roll center height, roll center gradient front to rear, and roll center migration, and how these elements affect the handling performance and balance of the car, how they can be used as tuning tools. We also dive into Ackerman steering, what that term even means, and how this can be used as well to help improve the performance of the car. Also, we cover subjects such as anti-dive and anti-squat. So this is going to be a very interesting chat for those who want to understand the suspension kinematics and vehicle dynamics of their car more intently. And of course, we also cover the various software packages that are available from Optimum G and how they can be used. And again, the fact that you don't need a PhD in order to be able to use them. Before we dive into our chat with Bruno, for those who are new to the Tuned In podcast, High Performance Academy is an online training school. We specialize in teaching people how to tune engines, build engines, construct wiring harnesses. We also cover race car setup, suspension, race driver education, 3D modeling and CAD, and fabrication, just to name a few of our subjects. You can find a full list of our subjects at hpacademy.com/courses. All of our courses are delivered via high definition video modules that you can take from anywhere in the world, provided you've got an internet connection, giving you the benefit of being able to learn from the comfort of your own place and learn at your own pace. Once you've purchased a course from us, it is yours for life. You can watch it as many times as you like. It never expires. And there is also zero risk purchasing any of our courses. You're protected by a 60-day, no questions asked, money back guarantee. You can also use the coupon code podcast75, and that'll get you $75 off the purchase of your very first HPA course. We'll put all of that information in the show notes to make it super easy for you to find. And now let's get into our interview. All right, welcome to the podcast, Bruno. Thanks for joining us today. And for a start, where are you joining us from in the world?
I am in Brazil currently, so I'm Brazilian and I have recently moved back here.
Okay, where is Optimum G based?
In Denver, Colorado, United States. So I lived there for a couple of years. Then I moved to Europe because most of my projects are in Europe. And now I'm finally back in Brazil, traveling a lot, but yeah, so a little bit all over the place.
Okay. All right. Well, let's roll things back a little bit. And I'm interested to learn a little bit about your background and specifically how you developed an interest in cars and more the high level sort of engineering aspect of the automotive scene.
Right. So actually, I'm not the typical car guy that liked cars as a kid. I just knew that I wanted to be an engineer, but no particular interest in cars. So I went on to studying mechatronics engineering at University of Sao Paulo. And there we have the Formula student or Formula SAE project. Are you aware of the project?
Yeah, absolutely. I think probably must have been about 30 to 40% of our guests so far bring up Formula SAE, and every time it comes up, I get jealous because I never had that opportunity here in New Zealand universities. But give us a quick rundown for those who maybe haven't followed the podcast or don't know what it is.
Yeah, so it's basically we as students, we design a race car from scratch. We build it and we race it. And by the way, I was one of the drivers, so I think you can be even more jealous now.
Nice.
And then we compete with different universities. So here in Brazil, we had another 40 universities to compete with our race car. We then won the competition. We went to the US, competed against another 140 universities from around the US, which was pretty fun. And I simply fell in love with race cars, with vehicle dynamics, with applying everything that I was learning in school directly to this project to make a car faster. And this is how I decided that I wanted to work in this area. Actually, all became concrete once Claude Ruel, my current boss, owner of Optimum G, came to Brazil to teach a seminar in vehicle dynamics. Once I was done with the seminar, I decided two things. Number one, that yes, I wanted to work with vehicle dynamics in race cars. And number two, that I wanted to work for Optimum G. And yes, so I applied for the company. I got the position even before I graduated, had to rush to graduate as soon as possible, moved to the US, and here I am today.
Okay, so straight out of your degree and straight into Optimum G. So again, just clarify, the degree that you qualified out of university with was?
Mechatronics engineering, which is basically to work with robots or robotics in general. And now I apply that to cars.
So quite removed from the specifics around vehicle dynamics, but I'm guessing there must be some crossover in there.
Yes, there is, but I think it's a very good example because so many people tell me I don't have an automotive degree in my school. I don't have any vehicle dynamics courses. Guess what? I didn't have any whatsoever, and I've never had any classes. I think in vehicle dynamics or automotive, I think the first one was really the seminar from Claude in Brazil. But nowadays, you have so much material, books, YouTube channels, and so on that you don't need that. So yeah.
Yeah, we have a lot of engineers come through the podcast, and I think if you've got basically any university is going to offer some kind of mechanical engineering degree, and that is a very, very broad topic. It's not necessarily centered solely on the automotive field, but once you understand those concepts, they can be applied to a specific field like vehicle dynamics.
Absolutely. So whenever I'm studying vehicle dynamics, I'm applying the physics and mechanical engineering concepts that I learned in school.
Sure. So the passion for applying what you were doing in university into the automotive field and then taking this vehicle dynamics seminar with Optimum G, am I right in assuming this is sort of born out of your Formula SAE work?
Yes, 100%. So I was the head and lead of suspension and vehicle dynamics. And after that, I became the lead of testing and data analysis. So it all started there.
Okay, excellent. All right, so let's talk a little bit about Optimum G and what it is. So give us a high-level overview of what Optimum G actually encompasses.
So Optimum G is the vehicle dynamics consultant. So basically we offer solutions involving vehicle dynamics. We have three main offerings. Number one is consulting, in which it could be as a race or performance or data engineer at the track with our customers, or it could be different projects. We have tire manufacturers hire us to help them develop better tires to match the vehicles. We have race car designers hiring us to design their suspensions and so on. Besides that, we also offer simulation software in the fields of kinematics, tires, and vehicle dynamics. And lastly, we teach seminars all around the world, two main ones, vehicle dynamics and also performance engineering. So this really connects with my trajectory at Optimum G. Now I am the lead performance engineer. So I am one of the engineers going to the track and coordinating our motorsports activities. And I'm also the head of consulting. So I'm leading most of our consulting projects, organizing our team, and so on. I also teach some of the seminars together with Claude, another colleague of mine. So different seminars are taught by different presenters. And it always started, now it connects to software, it always started with me as one of the software developers. So this is how I joined the company. And then I was moving more and more to the consulting and track performance aspects, which is what I'm really passionate about.
Okay. Now we're going to dive into those offerings that you've just talked about in a little bit more detail as we go. I'm interested with such a unique position. What's the day in the life of Bruno currently look like?
It's pretty fun, at least for me. I really enjoy it. So basically, either I'm traveling for consulting projects or for races. So now I live in Brazil, but I'm traveling to Europe, let's say every month for the races or for projects. So when I'm in the field, I mean, it's work the whole time, weekends, no days off whatsoever, going to the track since the race is on a weekend. But very enjoyable, meeting lots of different people, lots of different customers. Now, when I'm at home running the other consulting projects, my day looks like wake up early in the morning, go to the gym. I try to go to the gym every day. Then I come back to several meetings in the morning. So I try to run what we call daily meetings. It's typical in terms of engineering processes that you have daily meetings so that everybody can update or can give the updates on the different consulting projects that we're running. Then lunch. And in the afternoon, I try to have 1 hour call with several members of our team. So let's say that we are working in testing a tire for one of our customers in the rig, in the flat track. Then I'm going to have 1 hour call in the afternoon to review, okay, so how is the procedure that we're developing going? How are the tools that we're developing going? So I try to do that until late afternoon. And then I have the night to perform the work that I have to do, because in the consulting projects, I also have to do some work. And as you're going to notice very quickly, I love learning. So I try to also reserve a couple of hours at the end of the day to keep learning for upcoming projects. So that's what I pretty much do.
That sounds like you're packing a lot into the day. Good on you. Can you give us some insight into maybe what some of these consulting projects are? I'm sure there's a whole bunch of NDAs involved, but I mean, are you dealing with individual teams, maybe running a GT car or something like that, or are you working at OE levels with manufacturers, building bespoke race cars, all of the above?
Great question. Yeah, pretty much all of the above, but let me, even though I cannot give you names, I can give you some very good examples of the current projects that I'm running. Well, okay, so we work with specific teams. We obviously work with only one team per championship. We don't work with two different teams. But I have a couple of performance engineers who work with me. So we are currently doing GT World Challenge Europe. We are doing DTM. So we are leading the championship in GT World Challenge. We're doing pretty good in DTM as well. And we worked in Formula E, even though the season ended now. So these are the three championships that we are most working actively this year. And I'm coordinating some of them with my performance engineers at the track. Besides that, earlier this year, we had a race car manufacturer hire us to design their suspension, which is pretty nice, because the car is now hitting the track and we can see how the design will really behave at the track. Besides that, we have racing teams hiring us to test their tires in the flat track. So in the laboratory, you have a huge machine that you can mount a tire and test that. And we also work with tire manufacturers. So we are developing new tires for future championships. So I go to the track with them so that I am the vehicle dynamics and data analysis engineer for them. So they're working on the tire side. I'm working on the vehicle dynamics and vehicle performance side. So I'm processing all of the data, generating KPIs, metrics, and helping them to improve their tires for the following seasons. And lastly, we also work with OEMs. So not only racing, but we also do OEMs. So we are working in projects connecting tire performance with vehicle performance, helping them design better and safer cars.
It's a massive list you've just given us, and it's great because it does obviously give us immediate insight into the level you're working at and what you're doing. I'm interested particularly when we look at some of the larger teams, or specifically when we get to the OE level. Obviously at the OE level, money within reason is not an object. I'm interested why they would not look at having an in-house resource to offer the services you do rather than using an external consultant.
Yeah, no, that's a very appropriate question, because it is one of the challenges that we face, because many people, they want to build their own teams. So, well, there are two answers to that. Many times Optimum G is at a higher level than they are, and they don't have the time to build a team and they need quick results. So they are hiring us. Sometimes it's a one-off. Let's say, okay, so a racing team needs to perform a tire performance analysis, test different tires. They don't need to build a team for that. They hire Optimum G, and we solve all of their problems. And one thing that I would say it's an advantage of Optimum G compared to other consultants that we are happy to share our knowledge. So sometimes our customers also hire us for us to train them on how to perform such job so that in the future they don't depend on us anymore. So yeah, there are a couple of different reasons why they would work with a consultant compared to building an internal team for that work.
Okay, yeah, that makes perfect sense. I guess so far we've talked about some fairly high level concepts and we're going to go deeper down this rabbit hole. But before we sort of scare off half of the listeners, could you give us an idea of who could benefit from Optimum G's seminars and software? I mean, do you have to be a professional racing team or an OE manufacturer to get value out of this? Is a grassroots racer or a club level racer able to get value?
Oh, yes. So what happens is that when we offer direct consultant services to someone, typically it's at the professional level, just because of the cost. It's hard for an amateur driver to justify the cost, even though I have worked with some, for example, helping them fine tune suspension, stiffness, damping, driving analysis, data analysis, and so on. However, a lot of our products are also very, very useful for this type of racing, such as Optimum Kinematics, which helps you build and design a better suspension, such as Optimum Lab, which helps you understand the performance of the car and what trade-offs you should do in terms of powertrain and mass. Our seminars are a great source, especially if someone who is learning, who is improving, and who wants to keep growing. It's certainly a very good option as well. But it's interesting, Andre, because in our seminars, it's not only professional motorsport engineers, we have many students. So first or second year of engineering school, they're already in our seminar. So as long as the person prepares for the seminar and has some understanding of vehicle dynamics, they're going to get a lot of knowledge out of them.
Yeah, okay. No, good to get that clarity. I mean, one thing I'll add in here, which is one of the reasons we're talking to you today, is that we internally used Optimum Kinematics on our Honda CRX project. And I'll probably go into a bit more detail in how that worked as we go. And to be absolutely clear, no one inside of HPA I would class as a rocket scientist. There's no one with a PhD. You know, I think most of my guys, the guys particularly who are using that software, they learn to use it over the course of a couple of days, and they're just, average smart people. So I want to make that really clear that you don't have to have a PhD in order to gain value out of it. One of the things that I just wanted to talk about here with your seminars is, that's a catchphrase on your website: learn more in 4 days than a 2-year master's degree. So give us some background around that. How do you pack that in 4 days more than what someone's going to get in a 2-year master's degree?
Right. So actually, this phrase came from many people telling us. So it's not, we didn't come up with it. We had multiple people telling us. I learned more about vehicle dynamics specifically, of course, in your seminar than I did in my master. Well, for sure, it's a good thing for us. I'm not sure it's such a good thing for master's degrees, but in many cases, they're not focusing as much on vehicle dynamics, at least not to the extent that we would consider acceptable. And I would add another thing. They're not necessarily as concerned about how applicable that knowledge is. Why we are discussing setup changes. We're discussing, okay, so how do you make a car faster based on that? So of course, there are many master's degree with excellent vehicle dynamics courses, but oftentimes we hear that they're not as good. So this is why we have this phrase, just because we heard from multiple people. And how do we do that? Well, our seminars are pretty long, even though it's only 4 days, it's almost 12 hours a day. So it goes from 8 a.m. to 8 p.m. So in the end, it's 46 hours. Okay, you have lunch, 1 hour, you have a couple of breaks, but let's say 42 hours or 40 hours, which is a lot of content. Like if you stop to think about it, if you have 1 hour per 1 or 2 hours per week, how many weeks would take you to come to 40 hours of net content? Our material has been developed since the company started. So for the past 25 years, we have been fine tuning our vehicle dynamics seminars. So we just found the most efficient way of presenting this information so that people can make use of the knowledge. So it's not a binder or a book that you read and then you have no idea what to do with that. Every part of the project, there was a specific section that I would come back and just revisit the equations, revisit the concepts, and then improve my car based on that. So I think that's basically how we do it. And our teachers are very good. So Claude is an excellent teacher. I don't know if you had the chance to come to any of our seminars ever.
I have not.
Okay, Claude is an excellent teacher, extremely efficient. And I think that me and my other performance engineer, we just picked it from him. So we can teach in a very efficient way to give so much content, but in a digestible way so that people can really understand and retain this knowledge.
Okay. Now, you mentioned that you've had professional engineers come through and do your seminars and also students. I'm going to guess here that there is a base level of mechanical knowledge as well as a base level of mathematical knowledge that's going to be required before you would take one of these courses. Is that a safe assumption, or am I off the mark there?
Right. Yes. You don't have to be a genius, but you have to have some understanding of physics and mathematics. In many cases, you don't even need university level physics. Many times just high school level. If you master the basic physics laws and forces and so on, it's enough to understand the physics concepts. In terms of mathematics, yes, some skills. But I think more than that is just understanding engineering concepts in general. If you learned it, being it from school, high school, or by yourself. And I would say some vehicle dynamics background is very useful. So whoever is asking me, how should I prepare for the seminar? Can I come without studying anything? I would say it's not the best use of your time because you're not going to be able to retain as much. However, if you study some vehicle dynamics ahead of time, I'm going to give you the link for that later, but on my Instagram, I suggest all the vehicle dynamics books that you should study and which order. If you do like the first one or two, then you have a very good background to make the best use of the seminar and retain as much of the information as you could.
Okay, no, that sounds good, and it's always nice to have those resources as well for our listeners to be able to get into. Okay, let's dive a little bit more into the software. You've already mentioned the various software packages that Optimum G produces, but again, can you just reiterate those?
Yes, absolutely. So we develop Optimum Kinematics, which helps you understand and design the kinematics of your car. Then we have Optimum Tyre, in which you can get tire data and you can fit models or understand the tire models that are more and more commonly used in vehicle dynamic simulations. And then and by the way, we just released a completely rebuild of Optimum Tyre, which is called Optimum Tyre 2, which is an amazing software, really. We can talk a little bit about that if you want. And then lastly, we have Optimum Lab. So Optimum Lab is very interesting because it's a very simplified software, but even professional racing teams use it because it is useful. So we selected what are the most important parameters in car performance, and you only have them as inputs. So you have mass, you have downforce, you have engine power and engine curve or torque curve, and you also have gear ratios and you have tire grip. And with that, you can also model the track and then you can simulate your vehicle. And then you can quantify, all right, so if I change my car and I add 100 kilos, how much lap time am I going to lose? Or if I increase the power by 10%, how much lap time am I going to gain? And this gives you very quickly these answers. But it's so nice to see the most amateur driver, just enthusiast playing with the software just to learn how race cars work, how race car performance works. And then you go all the way up to professional motorsport engineers using the software because it is just a very good way to give you the fundamentals and the answers that you want.
We'll dive into that one in a moment, and we've used that software in the past to help choose gear ratios in the Hollinger gearbox that went into our SR86 endurance car. Before we get into that though, let's just come back to the Optimum Kinematics at the start. And we've, again, used this software in-house and found it to be exceptionally powerful and exceptionally valuable. And the reason I say it's exceptionally valuable is, in our case, it saved us wasting hours and hours, probably weeks of time, not to mention the cost of the materials that would have gone into the modifications we're making. So to give the very brief story here, we've got our Honda CRX powered by a naturally aspirated K20 2-litre engine. And what we wanted to do was move the engine back in the engine bay. I won't go too deep into why it was mounted where it was, but we basically could move the engine back about 100 millimetres, which seemed like a great idea. And we got into the changes that would be required to do that. We needed a chromoly subframe to mount the engine and the lower control arms, but that was fine. The problem we struck was that by moving the engine back, we had to completely relocate the steering rack. And when we relocated the steering rack, we modelled the suspension kinematics in Optimum Kinematics, and we very quickly found out that we were going to have a completely unmanageable bump steer. Like the car would have been an absolute pig to drive, downright dangerous. So obviously a complete step in the wrong direction. And we once we saw this, we went back and thought, okay, well, let's see for a start, what was our baseline? So we modelled the factory pickup points and looked at the bump curve or the toe curve as a result of that. And I mean, it might surprise some people, I think, would assume that properly designed suspension has zero toe change through bump and rebound, and that's probably not realistic. So there was some toe change anyway with the factory suspension, but we were just so far out of the ballpark, it was ridiculous. So then we started looking at modelling some options, and we could fix it by mounting the steering rack through the middle of the front differential, which obviously is not very realistic. Or we could have extended the steering arm out so that it sat in the middle of the wheel and the tyre, which of course again is unrealistic. So straight away you're like, right, well, we're boxed into this, we can't do it, it will not work. And, if we had gone through the process of moving that engine back, making the subframe, mounting the suspension, God forbid, just taking the car to the track and trying driving it, it would have been a disaster. So, that's just one aspect of like saving us time, not to mention actually going down the path of looking at various iterations of suspension design and seeing where you can get improvements. So that's my experience with it. And like I say, I mean, my guys who did that work didn't find it very difficult to build up the knowledge to use the software properly. Let's come back one step though. We've used this term kinematics. What's it actually mean? What is suspension kinematics?
Right. So basically, suspension kinematics is defining the wheel movement as well as a few other parameters such as roll centers that control load transfer. All right. So when you compress a wheel, it goes up and down. The camber is changing. This is kinematics. The caster is changing, the toe is changing. When you roll, your toe is also changing. All of that is kinematics. It is extremely important to understand what's going on because we know that in the end, everything is about tire performance. It's the only thing really generating force to move the car from one turn to another, to accelerate the car and so on. So we are trying to optimize the use of the tire. And you can only optimize the use of the tire by designing good kinematics and good motion and movement of your wheels. So that's basically it. And what the software tries to do is to simplify it. And actually, it's what everybody tells us. It's very user-friendly, very simple to work with. But it provides you an easy platform for you to model your suspension and then focus on these movements. You can move your car up and down in simulation and understand what's going on with the camber, what's going on with the toe, what's going on with the instant centers, roll centers, and so on. So this is one of the stages. It allows you to analyze your current suspension. The second stage, it allows you to optimize the suspension. And I don't know if you have played with it or if you guys have, but we have now the optimization module, which you basically tell the software, I want this bump steer, I want this alignment variation as I compress a tire. And the software can tell you, all right, if you want this curve, your pickup point should be up here, or this other pickup point should be a little bit more forward. So this would be from the design perspective. You can both analyze your suspension, or it can help you better design your suspension. One last aspect is that with the forces module, you can apply forces at the contact patch. Let's say we're cornering at 1G. You want to know how much or what's the stress in each of your components. The software can also calculate that for you. So when you make a modification to your suspension, you can understand how much more load you're getting because of this modification.
That in and of itself is a really interesting point because we've had guests on the podcast previously who are involved in designing and manufacturing components, usually via CNC, for example, or the 3D modeling process. And we've talked about FEA in that instance and how we can use that to confirm that the part is going to be fit for purpose, basically will support the loads involved. But the question there always comes back to, well, that's all well and good, but to use FEA, you have to tell the software what the loads are going to be, or the forces are going to be. If you don't know those, how do you estimate those? So, well, now we know Optimum G or Optimum Kinematics will allow that. So that's really interesting. In terms of the software pickup points, the suspension pickup points, though, I'm guessing probably a few listeners are thinking to themselves right now, well, that's all well and good, but how on earth do I accurately define these points? Because just like the FEA that I mentioned, this is very much a case of garbage in, garbage out. If we don't accurately have the suspension pickup points located as far as the kinematic software goes, all bets are off. Now, when we did this with our CRX, we've got the benefit of having a 3D scanner in-house. So the whole front end of the car is scanned, and we've basically been able to build the car in the virtual world using Fusion 360. Now, I'm absolutely aware that not everyone listening is going to have the benefit of a $10,000 or $15,000 laser scanner on hand. So can you give us some ideas on what the options are in defining these pickup points?
Right. So from our side, we have a couple of different options. Sometimes when we work with a car manufacturer, then we get the pickup points ourselves. That's the easiest. Then we have the lab testing, such as the ones that you guys use, such as 3D scanning. And you also have the 3D arms. So you basically mount the chassis, and then you have a 3D arm that is able to measure the pickup points and tell you the exact location. These are the most accurate. And then you have the not accurate necessarily, but more creative ways that people, they definitely find ways to measure that. So in that case, you need your chassis mounted to a specific location, but completely stable. Then you need to create some references. Let's say the front axle or the middle of the front axle is your reference. Then you have to split the measurement into different parts. You need to measure the lateral coordinate, which we call the Y. Then you need to measure the longitudinal coordinate of this pickup point. How do you do that? Well, the easiest is to do on the ground because it is flat. So what you could do is you could hang a rope with a weight, with a short weight, or with a little weight, and then you can measure the lateral coordinate and the longitudinal coordinate of the pickup point. And then the height is not that difficult. You can just take the measurement of the height of the pickup point, and in that case, you would have the pickup point location in 3D that you need for the software. Of course, you're going to face many challenges because the bottom pickup points are easy to be measured, or at least easier. The upper ones, you could have some other part, even the chassis, on the way. So you're going to have to be a little creative to calculate offsets and then to come up with new references to measure those pickup points. But we have a couple of different people doing the measurements themselves.
Yeah, I'm glad you mentioned that there are alternatives, albeit you're going to have to get a little creative. It's going to take a little bit more time. And I think it's fair to say if you're using the weight in a string, I was going to call it a plumb bob, which is a term that I think a lot of people will probably recognize. Accuracy, I mean, it's probably not going to be the same as our PL 3D laser scanner, which is probably going to be plus or minus maybe 0.1 of a millimeter. I'm guessing with a plumb bob, you're probably going to be within plus or minus 2 millimeters, but you do the best that you can, and it's going to still be beneficial. There's going to be a fair bit of work setting this up initially, but once you're done, then you can move into the software. All right, so with the Optimum Kinematics software, there's a range of terms that come into this, and I kind of just wanted to talk through some of these terms with you so that our listeners can get a really good idea of what the relevance of these terms are and how they actually affect the handling or the balance of the car. So one of the first ones I want to talk about is roll center, and specifically roll center height. This is a term that we hear very frequently when we're talking about vehicle dynamics. So for a start, what is the roll center height?
Yes, it's good that we discuss that because there's so much misconception around this concept. So the roll center height, or roll center, as the name says, it's the point around which the chassis rolls when it is rolling. So let's say that we're taking a corner. The car is going to roll around a specific point of the suspension. This is called the roll center. In this case, this point is coming from the instant center. So your left suspension will define one instant center, which is the point around which this left suspension rolls or moves around. So the left suspension is defining the instant center. The right suspension is defining the instant center. When you connect both of them, then you have the point around which the chassis is rotating. This is one of the definitions, but it's a simplification. So in reality, the car is not rolling or rotating about that point, but it's a good way to understand the concept of roll center. However, there is another, in my opinion, even more important parameter defined by the roll center, which is important for everybody working in terms of vehicle dynamics, car performance, or even car builds, which is load transfer. We know that when we take a corner, let's say a left-hand corner, we're going to have a lot of the load or the weight being transferred from the left side to the right side. A lot of it is going to go through the springs. This is why the car rolls, because it needs to compress the spring on the right side while extending the other. However, it's not all of the load transfer that is going through the springs. A lot of it is also going through the wishbones and through the links. So let's say that you are transferring 300 kilos. It could be that 150 kilos are going through the springs, but 150 kilos are being transferred through the wishbones and through the load, through the links, increasing the load on these links, and you could even get some failure on these links because of this load transfer. So the first one through the springs is called elastic load transfer because the spring is an elastic component. The second part of it is called geometric weight transfer. And this geometric weight transfer is defined by the roll center height. So if you have a really high roll center, most of the load transfer is going to go through the wishbones and the links. The advantage being the car rolls less. It's a little more stable. The platform is more stable. The disadvantage being you have a lot more stress on these components and you risk breaking them. So if you design a suspension and you make a modification and you increase a lot the height of the roll center, but you don't design your parts appropriately for that extra load, you can get suspension failures because of that.
Yeah, I think that would be something that could be quite easily overlooked as well. Now, you also mentioned another term there, center of gravity. There's a relationship here between the height of the center of gravity and the height of the roll center that is going to also impact the way the car will roll in a corner. Can you give us an overview of that, please?
Absolutely. So the most important parameter is not the roll center itself. It's the percentage of the roll center height compared to the CG height. So if you have let's say your CG height at 400 millimeters and your roll center height at 200, you can see that it's 50%. Therefore, 50% of the load transfer is elastic, going through the springs, and the other 50% is geometric, going through the wishbones and links. Now, my question back to you, Andre, is what happens if I have my roll center height at the same height as the CG? What's the proportion between elastic versus geometric lateral load transfer?
You're really putting me on the spot here. You know that you're the guest, not me, don't you? However, my understanding is if we've got the roll center height at the same height as the center of gravity, the car should not roll in the corner. Is that correct?
Perfect. And why it's not rolling? It's because all of the load transfer is not going through the springs, but instead going through the wishbones. So you see that everything connects. So yes, you have the lateral acceleration being applied at the CG, but if the point around which you rotate is at the same point, it's not going to roll. But in the end, it's all because the load transfer is going through the wishbones and through the links, not through the spring. So you see that everything is connected. The first concept is connected to the second concept.
These are all quite complex concepts for particularly those who have maybe never heard of them before. So I think it's probably one of these podcast episodes that's going to benefit from people reviewing and going and having another couple of listens until everything clicks into place. On that same note there, if we go to the other extreme and the roll center height was actually above the center of gravity height, the car would actually roll into the corner, which I mean sounds probably beneficial, but the reality is if you went that way, that's not what we want to achieve, right?
Right. But yeah, you're absolutely right. So you have the opposite behavior because you have the lateral acceleration below the point around which you rotate. So you rotate or basically you roll in the opposite direction. However, it does not mean that the load transfer is going to go in the opposite direction. The load transfer can only go to the outside tire. It's only the suspension that is rolling in the opposite direction.
Now, while we're talking about this roll center height versus center of gravity height, the other element that I just want to bring in here, which is a misconception, I guess, in the enthusiast market, is we lower the car and the handling is going to improve. And I think that's something that everyone getting into cars and looking at the ride height of the current crop of GT3 race cars would just assume. Lower ride height, better handling. But the reality is that some interesting things actually happen depending on your suspension geometry to that roll center height versus the center of gravity height when we lower a car. So can you talk about some of the nasty things when the geometry isn't correct and what happens to that roll center height versus center of gravity?
So let's say that you lower your car. You're not just taking the chassis, lowering it, and the suspension is staying in the same position. No, the suspension is also moving. So all your kinematic parameters are changing when you lower your car. In this case, why the performance improves? Well, if it's an aero car, it's obvious. It's because you get more ground effect. If it's a non-aero car, the biggest factor in improving car performance is because you lower the CG. If you lower the CG, you transfer less load when you are cornering and you have a more stable platform, more well distributed load on all four contact patches of the tires. However, as you all mentioned, you should also be aware of what's going on with the kinematics when you lower the car, because your roll centers will also change height, typically going lower. This means that you're going to lower how much geometric weight transfer you have, and you're going to increase the elastic weight transfer through the springs. Well, what's the difference? If you have the load transfer through the springs, it's slower because you see that the car needs to roll first before taking a set into the corner. While when you have a lot of geometric, it's an instantaneous load transfer. So the car is a lot more reactive. So you just have to be mindful that when you change the height of the car, yes, you're lowering the CG. That is excellent. And it's one of the primary factors in car performance. However, you're also changing how quickly you're going to transfer this load, depending on what you've done to your roll centers. Not only that, it could happen that you are changing more on one axle than the other. So you are changing how quickly you transfer the load on the front. Let's say you make it faster on the front, but slower on the rear. So this could also influence the handling of your car. So it's just very useful when you can understand what's going on in terms of your roll center heights when you make such a big change to your ride heights.
It's one of the problems we see with more production-based cars when they're lowered, and all things being equal, McPherson strut front suspension is probably the go-to for most OE manufacturers for garden variety cars because it's easy to package and relatively cost-effective to produce. And the problem with that is as we lower a McPherson strut suspension, generally, well, there's a couple of problems there. One is what happens to the camber. Maybe we'll park that element and come back to that shortly, but generally the roll center is going to lower much more than the center of gravity lowers. So you've sort of got this moment arm, I guess, between the roll center height and the center of gravity, so the car tends to roll more, and that's why there is also a range of correction products for popular cars for roll center correction and bump steer correction to kind of get the kinematics back close to where they were, but with the lowered ride height and the lower center of gravity. The other element you just mentioned there is the rear roll center height. So we've talked currently about one axle line on its own, but we've obviously got a front and rear axle, both with their own suspension kinematics and both, of course, then with their own roll center heights. So then if we're looking at the car sideways, we can actually draw a line through the front and rear roll center and get a gradient. So they're not always going to be at the same height. What's the importance of that gradient, and is that a tuning tool we can use to help with the car balance and handling?
Yes, that is for sure. So one thing that people like to do that I do not personally like is to create a roll. This should be your gradient. This should be the inclination of what we call the roll center or the roll axis, which is basically connecting both roll centers. Typically for race cars, or most of the time, we have the front roll center lower and the rear roll center higher. However, what I always like to emphasize to people is that there are so many parameters influencing car performance that it's not that if you change a little bit this rule of thumb that typical race cars use, that you cannot get good balance. I mean, you can play with springs, you can play with handlebars, you can play with adjustment to make up or to change that behavior. In any case, it is an adjustment tool because if you change the roll center of only one axle, you are influencing a lot the load transfer on that axle. So let's say that you decide that, oh, okay, let's say that you have too much understeer, which is typical for passenger cars. What could we do on the front axle? We want to decrease the load transfer because we know that if we decrease the load transfer on that axle, we get a more efficient tire usage. To decrease the load transfer, what can you do? You could soften your bars, you could soften your springs, but then you're going to start getting more movement. Or you could lower the roll center height. If you lower the roll center height, you're gonna get less load transfer on the front axle. Excuse me. And then as a consequence, I'm not gonna go into the details, you end up increasing a little bit the load transfer on the rear axle. But what do we get? Now we get a more balanced car because initially it was understeer. Now we were able to change the kinematics to influence the amount of load transfer on the front axle. We decreased it. We made the front axle a little more stable, a little bit more efficient, and now we have less understeer. So this is how you play with this gradient or the row axis in order to influence car behavior. So it's all about what's the change that you make to the front compared to the rear. This is why I mentioned when you lower your car, it is very interesting if you understand what's going on with the front also compared to the rear.
Yeah, sure. Now, you've just talked about making that change at the front axle. Am I right to assume that you could make an opposite change and increase the load transfer on the rear axle and have the same overall effect for the handling balance?
You're perfectly right. This is another typical misconception of vehicle dynamics that I tackle so much, or Optimum G in general, which is if you change the load transfer on one axle, you cannot lower the total load transfer of the car. You can only lower the total load transfer of the car if you change the CG, if you change the lateral acceleration, and you don't want to decrease the lateral acceleration, you want to increase it. You could decrease the mass, or you could decrease the wheel track. Unless you play with one of these four factors, you cannot change the total load transfer that your car sees when it's attacking a corner.
These are just the rules of physics, right?
Yes, exactly. The only thing you can do is to change the distribution of how much this total load transfer happens on the front axle compared to the rear axle. And this is one of the most important parameters defining mechanical balance. So if you have understeer or oversteer, one of the first questions we ask is, how can we change the load transfer? And as you mentioned, we could lower the front CG to decrease the load transfer, and it would automatically increase the load transfer on the rear. Remember, it's all about the distribution. Or conversely, we could do what you just proposed. We could increase the height of the rear roll center to increase the load transfer on the rear, which would automatically decrease the load transfer on the front. And this would be, at least in simplified terms, they would be equivalent solutions to combat this understeer that we're seeing.
Just the reason I wanted to bring up that option is obviously it's nice if there's a way of quickly and easily making a handling balance change during a pit stop. And just a race series that I was involved with here in New Zealand many years ago, it was a front engine rear wheel drive race car, production based, with a solid or live rear axle, and the mechanics had access to a screw adjuster through the rear deck lid, and basically in a matter of seconds they could wind that up or down and make a subtle change to the roll center height at the rear. You couldn't easily make that same change at the front, but that was an effective way of, making a handling balance change very, very quickly while, the other mechanics were maybe refueling or changing tyres. So, that's just something I wanted to point out there. At the moment, we've discussed this roll center location and kind of treated it like it's a fixed point, but the reality is that it is going to move around depending, again, on your suspension geometry, kinematics, etc. So what are we trying to design suspension that keeps that roll center as close to one point as we can? How much does the migration of that roll center during heave and roll of the race car actually affect the balance?
That's a very good question because you find pretty much no material explaining the matter on the internet. It's very hard to find. But basically, yes, as you were saying, once you break into a corner, once you corner, you're compressing and extending your suspension. You're moving your suspension, which is changing the kinematics. So as you mentioned, the roll center will be migrating. It could be going up, it could be going down, or it could be moving sideways to the left and to the right. So you know that it is always easier to understand a problem if we simplify it. In this case, what suspension design would be easier to understand? One where the roll center is not moving a lot. This is one of the reasons that we try to keep under control, because then we can better understand what's going on. We don't have surprises that, okay, the roll center moved so much sideways, now the suspension behavior is completely different. So this is the main reason why I personally try to keep it under control, just to simplify the problem. The second consideration, let's speak about roll center height. One thing that we need to understand is the following. Once the car goes up and down, especially if you make right height adjustments, or if it's an aero car that at high speeds is sitting at much lower right heights than at lower speeds, it is important that you understand how much your front roll center is going down proportionally to the rear. Are they moving the same amount, or is the front moving 3 times more than the rear, for example? And you gave some examples where this is very important. So this explains up and down. If it goes up and down, it's all that we discussed now. If the front is going down, it's going to induce more or less understeer. If the rear is going down, it's going to induce less oversteer, and so on. In any case, so this is the easy part because we already discussed that. Now the question is, what happens when the roll center is moving sideways? Well, to explain all the details, it will go back to physics and to load transfer equations. This is the biggest influence. But in any case, it's going to be a little less influential than the roll center height, that I can tell you. So with lateral movements, typically I'm trying to keep it within the wheel track width, let's say, but at least it's a little less influential than the roll center height. So if I can simplify everything, try to minimize the variation of your roll center, just to simplify the issue so that you understand your car, your build, your suspension. Focus mostly on vertical movement because it is the most influential, but also try to keep an eye on lateral movement just so that the suspension behavior is not changing as much from corner to corner or at different speeds or as you brake and attack a corner and so on. So this is how I would simplify based on how I design suspension kinematics.
Yeah, no, that makes sense. I'm guessing there in terms of the roll center height change as well, as you mentioned there, trying to keep the roll center height change or the gradient front to rear, that axis front to rear, kind of similar. That's going to be really important to make sure that the handling balance at low speed and high speed is similar.
I mean, this is the simple way of attacking this problem, and I like it. But when we design race cars, then we are not necessarily looking for the simple answer. So in reality, when I design a race car, I'm intentionally designing the variation of the front roll center and the rear roll center differently so that I get different behavior in low speed corners where I want a more agile car with more rotation compared to high speed where I want a more stable car.
Ultimately, I think the thing our listeners need to keep in mind is that suspension design, irrespective, is always just a set of compromises that we're trying to make the best choices. There is no black and white answer of this is the best geometry. It's not that simple, is it?
Yeah, you're absolutely right. So it's a compromise between, let's say, 10 main parameters or maybe 50 if you look at all of the parameters. It's a compromise, as you said. You have to find a trade-off. And remember what I mentioned, that I don't like creating rule of thumb or any rules for kinematics design because the car is all connected. If you have a different tire front to rear, it's going to ask you for a different kinematics compromise or a different kinematics difference between front and rear. So there is no perfect solution. However, at the same time, there's good practice. We should expect the camber variation to be in a given range. We should expect the roll center height to be in a given range. As long as you design like that the first way, then okay, then at least we are in a window that we can play. We can change the bars and adjust the balance. Or in the next iteration of the car, we can adjust a little bit more and fine tune. But it's all about iterations and trying to find the best compromise, keeping in mind this best practice in terms of kinematics design.
I just wanted to take a moment out of our interview with Bruno and talk about a course that is going to be really relevant if you're enjoying our discussion on vehicle dynamics and vehicle suspension kinematics, and that is our suspension tuning and optimization course. This is one of the topics that we've been asked for a huge amount of time, and it's a topic that I know a lot of people really don't understand because we often get asked two recurring questions. What spring rate should I be running? And how do I adjust my bump and rebound? Well, this course aims to answer those two questions, as well as hundreds more when it comes to the design and optimization of your suspension. We start with the suspension fundamentals. You'll learn about the purpose and role of the suspension and the different types of suspension you're likely to come across. You'll also learn about suspension frequency, which is one of the key elements that you're going to need to understand, along with suspension travel and motion ratios. We then move into springs, anti-roll bars, and bump stops and how these work. You'll learn about damper basics, the purpose of the damper, how they work, and how to tune them. You'll then learn about suspension geometry, in particular some of the topics that we've talked about today, including instant centers, roll centers, and the roll center axis, and also anti-squat and anti-dive effects. We'll learn about lateral load transfer basics and why this is so critical to the performance of the car. You'll also learn a range of practical skills such as measuring and calculating your center of gravity, motion ratios, anti-roll bar stiffness, how to choose the correct spring rate for your particular platform and application, as well as choosing and tuning anti-roll bars and tuning your dampers. Included in this course is a comprehensive spreadsheet that takes a lot of the difficulty and complexity out of these calculations for you. You simply enter the values that you're going to measure from your car, and the spreadsheet will do all of the hard work for you, making it very easy to start optimizing your suspension performance. This course is normally valued at $149 US. You can use the coupon code OptimumG50. That's going to get you 50% off that particular course. And even using that code, you are still protected by our 60-day no questions asked money back guarantee. So if you purchase and decide it's not quite what you expected, no problem. Let us know. We'll give you a full refund of the purchase price. Let's get back to our interview now. All right, well, let's move on from roll center, and I'll admit we probably started in the deep end there. Roll center, if you haven't heard of it before, and particularly without the benefit of diagrams, and we'll actually put some diagrams in the show notes so people can research it a bit more if they want. It is a difficult concept to get your head around, but let's talk about one that I think people will probably understand a little bit easier, which is camber, more specifically camber curves and camber gain. And what we're talking about here is the vertical angulation of the wheels, and it's all really about, again, trying to optimize our tyre contact patch on the track, make the most of that tyre and get the most grip that we can. But of course, again, as the suspension goes through compression and rebound, the camber is constantly changing. So can you talk to us about, first of all, maybe the differences between a McPherson strut suspension and a well-designed double wishbone suspension in terms of how that affects the camber gain or camber curve?
Yes, basically when you have the multi-link suspensions, or for example, double wishbone suspensions, in summary, you have a lot more control over the camber curve. So not only you can get better camber curve in general, but you have a little bit more freedom in designing this camber curve exactly the way you want. What do I mean by camber curve is how much camber variation you have as you compress your suspension. In any case, we can also find very good solutions in McPherson suspension. So it's not that you should have only double wishbones, even though race cars are typically working with double wishbones because of the freedom and the fine-tuning perspective and opportunities that you have there.
With the double wishbone, my sort of understanding of a way of explaining this is well designed with the right camber curve, we can run less static negative camber. So when the car is stationary, we don't have to run so much negative camber in order to achieve the desired negative camber when the car is cornering hard and the loaded tyre is compressed. Versus McPherson strut, we don't tend to gain as much or be able to gain as much negative camber during compression as a double wishbone suspension. So hence we need to run more static negative camber. And the downside of that is it's going to influence or reduce the grip in a straight line. And by that I mean under acceleration and braking, we've got less of the tyre contact patch on the ground. Is that a fair way of representing that?
Yes. So just to finish your last point, that what are the disadvantages of running a higher static camber? Not only you have less grip in braking, but you are stressing a lot more the inside shoulder. So for race cars, that can be a big problem because you can even fail tires especially when we're working in endurance and so on. So we are trying to minimize how much static camber we need so that in straight line, we're not stressing the inside shoulder as much. But at the same time, what matters the most for the performance is how much grip you get in the corners, you have in the corner. So you still need to have some sort of negative camber so that you have perfect contact patch, let's say, when cornering. But well, let me explain all of that. If we go back, let's again, we are taking a left-hand corner. We transfer the load. We can all imagine that the car is rolling to the right side. But the thing is, it's not only the chassis that is rolling, the tire is also rolling together with the chassis. So if you had a tire, let's say camber zero, completely straight, once you roll, it's going to go towards what we call positive camber. And positive camber is definitely not ideal for grip because the contact patch, you don't have a very well distributed contact patch. You're not using all of the tire width. You're only using the outside shoulder. Not only that, but when you have, let's say, negative camber, which is the good camber, you have what we call camber thrust. So it's not only about the area of the contact patch, but once the tire is already pointing the direction of the corner, you're already gaining some grip in that direction. In any case, if when we roll, we gain positive camber, which is what we do not want on the outside tire, in this case, the right side, we need some static negative camber. So let's say that when rolling, we were losing 1 degree of camber. Maybe we need 1 degree of static camber. But what's the interesting part here? The camber variation is not only defined by how much roll you get, it's also defined again by your kinematics. So if you change your kinematics, you can lose, let's say, or you can gain less positive camber when you're rolling. So now instead of gaining 1 degree of positive camber, which is something that we do not want, if we optimize our kinematics design and we change our camber curve, now we're only going to gain half a degree of positive camber. So while in the first scenario, we needed a static camber of 1 degree, now we only need half. If we go for the extreme case, if you design a really bad suspension, you could be gaining up to 2 or 3 degrees of positive camber, which is terrible for the tire. You need to run a lot of static camber. And in an optimized suspension, you could expect to lose half of that. So you can decrease by half the static camber that you're using. So you can gain straight line, but you can also gain in cornering. And you also get a more well-distributed tire wear along your contact patch.
Okay, perfect. I think, like I said at the start, the camber side of things, probably a slightly easier concept for people to get their head around. But I think there's a lack of understanding. Obviously, people who have been to racetracks will see that cars have negative camber, but why we need that negative camber and why some cars can get away with less or maybe need more is something that goes a little bit deeper. So thank you for that description there. Let's move on to another element which sort of goes hand in hand with this, just as the suspension moves through its bump and rebound travel, is the toe curve, or another terminology for that would be bump steer. Basically, whether the wheels will start tracking inwards or angle inwards or outwards as they go through bump and rebound. So I mentioned, I think a little earlier, most people would probably assume that a well-designed suspension system, we would have zero toe change as the wheels move through their travel. The reality might be something different. Is the desirable elements of toe change that we are trying to achieve with our suspension?
It actually goes to the exact same discussion as the roll center. Whenever people are designing a car for the first time, I'm going to recommend that they design for a no bump steer, meaning that as you compress up and down, the alignment is not changing. Because this is the simple way, it's very easy for you to understand what's going on with your car. Now, when you're trying to fine tune and design a winner race car, then you are starting to play with the nuances. So not necessarily we want zero bump steer when we're designing a car. We want the bump steer that it needs to have ideal balance. So let's say that the previous iteration of this car had a lot of instability under braking. Maybe we're going to design a bump steer that whenever the car is braking and going up, the rear axle is going toe in, meaning that the tires are pointing inward, increasing the stability of the rear axle. Or when it's cornering, you can have the rear tire, if you need more rotation, when it's cornering, the outside tire is going toe out, for example, on the rear, which helps you get more rotation on the car. So it all depends on what you want to achieve with that particular car. So it's not necessarily the case that bump steer is bad. However, for 95% of the time, I'll tell people design a car with minimized bump steer so that you understand your car, you understand the car behavior, and you have no surprises when you're running it at the track. So it all goes back to the example that you gave. When you make a suspension change, The first thing you should keep in mind, even before roll centers, even before camber curve, is the bump steer. If you have very bad bump steer, particularly on the rear, which is even more influential than the front, you could have terrible car performance, terrible car handling just because of that. So whenever you make a suspension change, ideally run it in the virtual world, such as with Optimum Kinematics, so that you can anticipate what's going to happen and optimize your bump steer. Or the least you should be doing is in your workshop, design a system that you can move your suspension up and down and measure the angle variation, the toe variation to understand how much bump steer you have after a change. Because this could explain all the balance issues that you're going to get at the track.
I absolutely agree. I think understanding what you've got in terms of a starting point is really, really critical. Just sort of coming back a step though, we talked about camber and how the camber curve will influence the amount of static negative camber that we need to run. But I think probably we've got a similar situation with toe curves as well. Let's try and simplify. So generally we sort of will find that if we run a small amount of toe out on the front axle line, that tends to aid turn in into a corner. And the problem with that, though, is that if we're running a lot of toe out, then in a straight line, and particularly at high speed, that creates a lot of scrub, which will reduce our top speed and basically put a lot more stress on the tyre. So ideally for straight line performance, we would like zero toe. But of course, then as we get on the brakes, compress the front suspension and begin to turn into the corner, we would like to move to a little bit of toe out. Likewise, at the rear of the car, again, in a straight line, we would like zero toe, but as you've mentioned with braking stability, if we happen to be at zero toe and there's some compliance in the suspension bushes, that may move to toe out, making the car very unstable, or we've got a toe curve that moves towards toe out as the rear of the car moves into rebound and lifts up, obviously undesirable. So by properly designing this, you can get a toe curve that allows you to run with more zero toe, less scrub in a straight line, but still get the desirable elements under braking and cornering?
That's it. Yeah, you're completely right. Some interesting parameters that the rear toe is pretty straightforward. As you run more rear towing, you're going to get more stability and less rotation of the car, which is good when you have an unstable car. The front toe, to be honest, it changes from car to car. There are some cars that will be benefited from running toe out, some cars that will be benefited from running toe in terms of how much response they get. But yes, that's the idea. Bump steer will influence the dynamic toe, just like we have the dynamic camber, we have the dynamic toe, which is in the end defines the car behavior. So yes, you're right in what you stated. One thing that you mentioned that I think is particularly important for us to mention, to highlight, is the importance of bushings. Because it's not only about the kinematics, it's also about the compliance. Because if you change your bushings, you can change how much camber variation you get from compliance. You can change how much toe you get. So it's pretty interesting to keep that in mind. After going from a high stiffness to another high stiffness, the change is going to be minimal, but it's just something that you should keep in mind in case you change from very soft bushings to very stiff bushings. Most of the case you're going to improve. Typically, as you reduce compliance, you're going to improve the kinematics. But if you go the other way around, then it could be dangerous. Then you could start getting a lot more bump steer than you would expect dynamically at the track.
Of course, if we're talking about professional race cars or even sort of most higher end club level race cars, we typically get rid of rubber bushings and we'll move to a spherical bearing, which maybe doesn't entirely eliminate compliance, but certainly gets rid of it. But it's probably a big topic in and of itself. But probably the important point here to note is that it is a real thing and it is going to affect your geometry on the track, and depending on the bushing type, that will also affect how much it changes. Now, another topic that I wanted to pick your brains on here, and this is one I've really struggled to find much information on its actual relevance, and a lot of the information I see is actually conflicting, and this is Ackerman steering. And again, unfortunately, very complex in terms of explaining what Ackerman steering is. Hopefully you're going to have a nice, easy analogy for us. But again, hopefully we can also put an image in the show notes so that people can review that and get a better idea. But Ackerman steering, high level, what is it? How relevant is it? And what do we need to know about it?
Here we go. So Ackerman is the difference of steering or alignment between the inside tire and the outside tire. So again, we are going for we're taking a left-hand corner. The inside tire would be the left side. The outside tire would be the right side. So what's the difference in steering that you get? The extreme case, which we call Pro Ackermann, would be the inside tire steering a lot more than the outside tire. And the opposite would be anti-Ackermann, where we would have the outside tire, meaning the right side in this case, steering a lot more than the inside tire. So first of all, how do you get this difference? Again, it's all coming from kinematics. Depending on the angle of the link, so for example, or the steering rack position, it's gonna influence the steering on the left side versus the steering on the right side. Why is it important? Well, it's easy to explain why it's important because we just explained how crucial toe or bump steer is. So if you have any variation, it's going to influence a lot the car behavior, even more than camber. And the Ackermann is directly defining that. So as you steer, you basically have a variable toe. So you can put a dynamic toe out if you have pro Ackermann or a dynamic toe in if you have anti Ackermann. So it is very important because the toe defines the slip angle, which is how much you are slipping the tires, which directly defines the tire forces. All right, so I think it's clear why it is so important and why it's so influential on car behavior. But now, which one is better, pro Ackermann or anti Ackermann?
Well, this is the conflicting element, isn't it? The $1,000,000 question.
It is. It is. And you should expect no different from me, but I cannot tell you which one is better. It depends on multiple parameters. Just to list a few, the car itself, so its dimensions, weights, the tires that you're running. There are some tires that ask for a more pro Ackermann, there are some tires that ask for a more anti Ackermann, and also the type of racing. If you're running very low speed corners or very high speed corners, they are going to ask for different Ackermann numbers. All right, but now, why do we want, first of all, why do we want in the first place to steer differently on the inside tire and the outside tire? It is basically because the outside tire will be more loaded compared to the inside tire. And a tire that is more loaded could ask for a different slip angle compared to the tire that is less loaded to generate peak grip.
Coming back one step though, something you haven't mentioned, which I always see in discussion on Ackermann, is the inside tire. And in your example, we're turning left, so that's the left-hand tire. That's actually if we sort of drew a circle around a central axis or central point, and then we drew another circle for the outside of the car. Obviously, depending on our track, the outside tire, the radius that's moving through is not as tight as the inside wheel. So that's sort of the argument for Ackermann that I've seen. Is that a reasonable element to discuss?
Yes, for sure it is connected to the discussion, but it's an oversimplification, let's say. In any case, it's very good that you bring up this concept because when we say perfectly Ackermann or 100% Ackermann, it is basically because we're following what you described. If we take the center of the corner and we draw a circle connecting to the inside tire or a circle connecting to the outside tire, we see that the inside tire will steer a little bit more. It needs to steer a little bit more than the outside tire. And yes, there is some validity to it, but it is a simplification because we have a couple other parameters. All right, so the next parameter is what I just described. Tires with different loads will ask for different slip angles. So let's say that your outside tire asks for a higher slip angle. It needs more slippage when it's loaded. It is asking for what? For an anti-Ackermann geometry because it is trying to put more, it's asking for more slip angle or more steering on the outside tire compared to the inside tire. But then you go for other tires that ask the opposite. They want more slip angle for the inside tire compared to the outside tire. In that case, it would ask for pro Ackermann. In any case, it is very hard for us to know what our tires are asking. So what I'm going to give you is some advice on, regardless of the tire, what approach you should use to try and determine the best Ackermann for your vehicle. So first of all, it depends on the type of racing that you're doing. A rule of thumb is the following. The lower the speed, the more rotation the car needs. We obviously need a lot more rotation, low speed corners compared to high speed corners. The more rotation you have, the more pro Ackermann you need. Because naturally, as the car takes a corner, the slip angle on the left side and right sides are not the same because of the dynamics of the corner. Regardless of Ackermann, regardless of the steering, they're not the same. And the lower the speed, the more pro Ackermann you need to have both tires at the same slip angle, which is a good bet. Whenever I don't know, is this tire pro Ackermann, is this tire anti Ackermann? I don't know. Let's go for the same slip angle on both sides. So the same slippage on left and right sides. So in that case, the lower the speed, the more pro Ackermann you should have. And for example, when you go to Formula student competitions, I don't know if you're familiar with the circuit, but it's very low speed. That project that I was discussing in the beginning of the episode, it's very low speed. Typically, even if your tire is asking for anti-ackerman, typically a pro-ackerman approach will give you more front grip, and it's all about maximizing the front grip. The higher the speed, then you can go towards more anti-Ackerman because naturally you're not putting so much slip angle, or the dynamics of the corner are not imposing so much slip angle on the outside tire. So you can have a more anti-Ackerman approach, or more, let's say, parallel steering, which is another approach that we didn't discuss. So this is number one. And then another very efficient way to determine if your car, and I think you're going to like that one, to determine if your car needs pro Ackerman or anti Ackerman, you need to find a pretty big parking lot or testing area or a proving ground where you can do a skid pad in a radius that makes sense for whatever type of racing you do. How can we simulate Ackerman? Remember that I said that pro Ackerman is as if you put dynamic toe out, and anti Ackerman is as if you put dynamic toe in. You can simulate an Ackerman geometry not by changing the pickup points, but by simply changing the toe. So you can do the same skid pad with toe out, with toe in, and then it's on you or on the data analysis to understand which one gave me more grip.
That's a really good tip.
Because basically you're simulating the Ackerman without changing anything on your suspension. Once you understand, okay, it seems like if I put more toe out, meaning that I decrease the slip angle on the outside tire, I'm gaining grip. All right, if I'm putting toe out, this is the equivalent to pro Ackerman. So maybe my car needs a little bit more pro Ackerman than I currently have. So this is a very good way of testing on track what your car is asking for.
Yeah, that's a great takeaway. I would not have considered that, because typically, at least when we're dealing with production cars, actually making changes to the Ackerman is not a simple task. So it's not something that you're going to be able to go in and make 5 changes with at the track and kind of get a sense. So having that ability to see what the car actually wants and then allowing you to then make the hardware modifications to actually achieve that, definitely going to be a big time saver.
And I have one last suggestion in terms of Ackerman. For those designing the car, especially the upright, you can design multiple pickup points as long as you use a kinematic simulation software where you have pro Ackerman and anti Ackerman. So whenever someone asks me, what Ackerman should I use, especially if it's a race car manufacturer or a Formula student team, I tell them design both and let's test it at the track, because as I said, it's such a complicated subject, but I'm not even going to take the time to explain that most of the times it's a lot more efficient if you test it at the track compared to just theorizing what goes on behind all this theory.
Yeah, absolutely. Another thing I just wanted to come back to is a term that you have used quite a bit just there, and just for the sake of clarity for those who aren't sort of following along, slip angle. In relation to the tyre, what does that term mean?
So whenever you're taking a corner, your tire is not sliding the same direction as it is pointing. So for example, the front tire, you are steering at 10 degrees. The tire is actually not going that direction. It's going at a 5-degree different direction. This 5 degrees is exactly the slip angle. So it's basically the sliding of the tire. So it's the sliding angle of the tire. And tire forces are all about this sliding angle. Same on the rear, even though it's pointing straight, the rear tire is not going in that exact direction. It's going at a 5-degree angle or at a 10-degree angle, which is exactly the the slip angle. And this slip angle is what is generating tire forces. So that's why we're trying to find what's the ideal slip angle to maximize tire forces. That ideal slip angle could be different left and right side. That's why we play with the Ackerman geometry, exactly to put each of the separate tires at their ideal slip angle.
Okay. And that ideal slip angle, as you've also mentioned, just to reiterate, is going to vary from one brand of tyre or compound of tyre to another as well.
Right. And just to give a very concrete example, whenever you have a more reactive tire, it is probably not only because it has more grip, but also probably because the ideal slip angle is lower. If we need a smaller slip angle, the tire will be a lot more reactive because you steer just a little bit. It is already close to the ideal slip angle. It's already generating most of its grip, or it's already maximizing the grip. So when you go from a typically passenger car tire to a sports tire, your slip angle, just to give you an idea, your ideal slip angle is coming from 10 to 15 degrees for a passenger car tire down to 5 to 7 degrees for a sports tire. That's why it's a lot more responsive.
Yeah, no, that makes perfect sense. All right, I think we could go on forever on this topic. There is two more elements I do want to discuss in terms of the suspension, and that's the terminology anti-dive and anti-squat. What do these mean in terms of geometry? And again, can you give us any guidance or any rules of thumb? Again, it's one of those elements that there's quite a lot of conflicting information around.
Yeah, so actually it's going to be easy to explain because we already discussed roll centers and they are the equivalent of roll centers, while roll centers are defining the load transfer laterally, so lateral load transfer. The anti-dive and anti-squat are defining the geometric weight transfer or the load transfer longitudinally. So let's go back to our example. Remember that we said that we had a CG of 400 millimeters, while we had a roll center of 200 millimeters. This is a split of 50%. Guess what? This is the equivalent of a 50% anti-dive. In this case of the roll center, when we were taking a corner, we knew that 50% was going through the springs and the car was rolling because of that, while 50% was going through the links and the car was not rolling because of that component, at least not on the suspension. Anti-dive and anti-squat are exactly the same. So when you tell me I have 50% of anti-dive, this means that when you're braking and transferring load to the front axle, 50% is going through the springs, causing the car to pitch more because you're compressing the springs, while the other 50% is geometric and is going through the links. And you are not pitching because of that. So what's the advantage of running high anti-dive? The car is pitching a lot less. You can run the car lower because it's not going to touch the ground. You have quicker load transfer, so everything is more stable. The platform is more stable. What's the disadvantage? Well, first of all, there is a lot more load going through the links. So if you're getting a lot of suspension failures, you should ask if it's because either you have too high of an anti-dive, or you have not designed your components appropriately for those loads for that specific anti-dive. So this is the disadvantage. You have so much load transfer through the links that you can start having suspension failures. And one last thing is that for beginner drivers, if you have a little bit more suspension movement, it's better because they have more time to feel the car. When you go to race cars, then you have a lot higher anti-dive because the drivers are so good that they don't need any time to think. They can have this instant load transfer through the links instead of a slowed load transfer through the springs. But that's why you would run higher or lower anti-dive, and the equivalent would be anti-squat when you are back on the throttle instead of braking.
Okay. So, I mean, just like everything, no real black and white here, just different shades of grey, but depending there on the driver. I mean, I'm guessing in terms of the mechanical strength of the suspension components, that's relatively straightforward. I mean, they can always, of course, be designed to cope with more load. The parts just end up larger and therefore heavier, and obviously weight's the enemy of performance when it comes to race cars, but it sounds like a lot of it really is going to come down more to the driver's preference and driver's skill level. Is that fair?
Yes, not only driver, but also the goal of your car. If it's an aero car, you could afford running higher. You could want to run higher values so that you don't have as much platform variation, which shift the downforce from the rear axle to the front axle. So yeah, there are a couple of different parameters. It all depends how responsive or you want your car and how much platform control. In any case, I don't like giving a final number because there is no final number. I can tell you what's typical for a race car. For a race car, typical number is between 30% all the way up to 100%. That's the typical number for a race car. For anti-dive. For anti-squat, a little bit lower, typically from 20 to 60% is a typical range for a race car.
Okay. So would A, building enough adjustability into the suspension to move the geometry like that be beneficial? And then B, those ranges that you've just said, is it safe to assume that starting somewhere in the middle of those ranges for anti-dive and anti-squat would be a fair place to start our testing and then try varying it and seeing how the performance changes?
That's what I would do. Yeah, I would be happy with that. That's what I do when I design a race car. I start there and then I understand what the car needs for further changes.
All right. Let's park that and move on. Like I say, we could probably talk for another hour on it, but I think we've covered like some of those key concepts there, and hopefully that's reinforced their importance to our listeners. The next piece of software I want to talk about is Optimum Lap, and you've really kind of given us a brief sort of understanding of what that is. You can model the car and get a sense of making a change to this parameter is going to give us this result in terms of lap time. Now, obviously, the race car is an incredibly complex thing. and you've said that you've simplified it down to the key inputs that you've found are necessary. And again, comes back to this garbage in, garbage out element, and breaking it down so it's easier for the user to actually come up with the right numbers to put in to get sensible results. So could you give us an idea of what data is required to use Optimum Lab?
Yeah, so basically we identify the primary contributors to performance, and these are the only ones that you have to input in the software. So as we know, the weight of the car, so the mass. Then after that, we have tire grip, which is extremely important. Then we have downforce and drag. Then we have engine curve. And then we have gearbox and gear ratios. That's pretty much all you need to run simulations in Optimum Lab. And why is it so effective? Because these are the primary contributors to performance and to lap time. Everything else is just fine tuning how you can exploit the tire grip to try and increase this tire grip a little bit more or try to gain a little bit more downforce. But all of those are secondary parameters. Besides that, we need to build the track, right? Because it's one thing having the car, and then the second thing is having the track. So you have basically two options in Optimum Lab. Either you build it manually. You can say, okay, first I have a corner with this radius and so on, which is a pretty tedious work. But the good thing is on our website, you can upload real data of very basic sensors. You only need speed, lateral acceleration, and distance or time. That's pretty much it. And it can convert this real data to a track map. Then you can import this track map into the software. Now you have the car, very simple car, very simple track, and you can run simulations to understand what's the car performance.
Great. That was one of the questions I was going to get to, is how on earth do we build track maps? Because that in and of itself is a pretty big job if you want to be accurate. Okay, so coming back to those parameters, some of them I'm sort of thinking pretty easy. I mean, the weight of the car, not very difficult to get that. Likewise, I mean, anyone who's had their car tuned, the torque and power curves of the engine, pretty straightforward. Gear ratios, again, pretty straightforward. Aero, that's a little bit trickier. If you're buying aero components from a higher level manufacturer, they're probably going to be able to give you data on downforce versus drag. A little bit difficult to get maybe on some of the more, let's say, homemade components. But the key one that I'm sort of wondering about is tyre models. And you've talked about the tyre performance and tyre grip. And how on earth are we supposed to come up with this data? That sounds like it's complex.
It is not. Actually, it's as simple as the other ones, at least in Optimum Lab. So we don't require a complete tire model. We only require tire grip. And there are two ways that you can identify the tire grip, which would be basically the peak grip of the tire. Number one, you can take a typical number for this type of racing or for this type of tires. So we know what number we should expect for a racing leg, for a passenger car tire, for a sports tire. The second way, which is what I do and what I recommend people doing, is the following. Many cars, you are logging the lateral accelerations and the longitudinal accelerations, right? How do you get to those accelerations? They are basically because of the grip of the tire. Therefore, what I do is the following. I run the first simulation in Optimum Tire. I extract the results. I plot them, let's say, in Excel. I get my real data. I also look at it. And let's say that my peak deceleration under braking was 1.3 G on the real data. But in Optimum Lab, I'm getting 1.5. What do? I tune it down a little bit, the longitudinal coefficient of friction, until I can get to 1.3, matching the real data. Then I look at the apex. At the apex, when cornering, I'm taking 1.1 G. But in the simulation, I'm taking only I'm reaching only 0.9 G. So I can increase a little bit the factor until I match the data. And once you have it matched, then all of the work after that, I have to say it's pretty accurate. So if you do this initial validation of getting downforce right, of getting tire coefficients right, anything that you do after that for the primary numbers, such as mass, engine curve, gear ratios, and so on, will be pretty accurate, will be more or less what you see if you do that at the track. So it is a really nice way of identifying, okay, if I increase is it better if I invest money in decreasing my car weight by 50 kilos, or should I increase my power by 5%? You can actually simulate that in Optimum Lab with minimal inputs, and you're going to get a very accurate answer.
Okay. Yeah, that breaks it down into something that sounds relatively manageable. And again, you don't have to be a rocket scientist in order to be able to actually generate the inputs and get useful data. The obvious question is here, how accurately does this validate to real world performance when these changes have been made and the car's taken to the track?
Very good. Like maybe if it's just a weight change or something like that, I can guess an accuracy of 1%. It's really straightforward.
Oh, wow.
Yes. The only thing is that in real life, if you change the weight, but also the weight distribution, this will change car balance, and then it's going to be a lot more than 1%. So if you, in real life, if you're able to simplify and keep the same weight distribution, only removing mass, or if you can increase the tire grip by 1%, the results would be pretty accurate. Let's say between 0 to 5% accuracy is what I would typically expect, as long as you can really model what's going on. Because let's say that you think that you change your engine power by 5%, but actually your curve changes slightly. If you, as you said, garbage in, garbage out. So as long as you can really model what happened on the real car, the accuracy will be pretty high if you do that first phase of validation of the aero parameters and also the tire parameters.
Yeah. Okay. Right, let's move on to Optimum Tyre. So again, you've given us a high-level understanding of that. And this is one of those areas that I'll admit I have not dived deep into. And every professional race engineer that I talk to, it always comes back to a conversation around how complex the tyre is and how important understanding the tyre is to getting the performance unlocked from the car. And I mean, obviously, ultimately, no matter how much power we've got, how much downforce we've got, how much money's been poured into developing the car, ultimately, it's those 4 tyre contact patches that really make or break that ultimate performance of the car around a racetrack. So give us an understanding of what data you're generating from a tyre and even sort of how that's achieved.
So there are 2 ways of understanding the tire, and at the professional level, we try to use both. The first one is testing the tire in a lab. So as I mentioned, we have a machine that is called a flat track machine, which is a huge machine where you mount your tire as if it was a car. There is a rolling floor, and then you can steer, you can add or remove load, you can change the pressure, you can change the camber, and you can measure what's going on. So you try to quantify the tire in all different possible conditions and combinations of load, camber, slip angle, and so on. And you measure and you log the forces and moments being generated. Then you take all of this data, you put inside Optimum Tire, and Optimum Tire will help you process this data. Once you process and make sense of the tire, all right, so the tire ideal grip is in this temperature window, which is a test that we can do in this type of flat track. The ideal slip angle is 5 degrees. The ideal pressure is 1.8 bar. Once you've done all of that, you can then create a model on top of that. So you don't depend on the raw data anymore. You have a mathematical model that you can put in any vehicle dynamics simulation software. After that, you can run simulations to understand, right, first I had only my tire. Now I have the whole vehicle. What can I do to the vehicle to optimize the tire performance? Okay, so this is from the aspect of testing the tire in a lab and then running simulations. The more practical approach, which is not replaced by the lab tire at all, is to optimize the tire at the track. And this is where the work of a performance engineer, such as myself, or even a tire performance engineer, which is another role that I play, this is what we are doing at the track. We are trying to analyze dozens of different sources of information to understand how our tire operates and how we can optimize it. Meaning, what's the ideal temperature that we are looking at, that we should try to achieve? What is the ideal pressure or the ideal pressure range? What is the ideal dynamic camber? What's the ideal, even Ackerman tool that will optimize tire usage, slip angles, tire temperatures, all of the same time? And on top of that, especially when you're running endurance races, you need to look at performance degradation, so tire wear and tire thermal degradation. So we are measuring the tire wear in all the different measurement holes to understand wear distribution and understand, okay, we have a very asymmetric wear, meaning that we're not using all of the tread, all of the tire performance. What can we change on the car setup to optimize and make the tire more consistent with a more distributed tire wear on the contact patch? So these are the 2 different approaches that you have in order to better understand your tires: lab simulation and then track analysis.
All right, so the lab simulation, obviously for probably 99.9% of our listeners, maybe even 100% of our listeners is probably not practical or realistic. But some of the concepts that you talked about at the track, these absolutely are. Can you give us a little bit more insight there? Like, what input, what data are you relying on here to help optimize these elements? I mean, obviously tire pressure is easy to monitor and check. Are you looking at tire pyrometer readings when the car comes back into the pits? Are you looking at live infrared tire temperature data on the tread across the tread width while the car's on the track, sort of what that's doing dynamically, or is it all of the above?
So let me give you a few examples of what a tire performance engineer is doing at the track, because it's going to give you very applicable traits or methods for you to optimize the tire usage of your car at the track. So first of all, yes, we were discussing what we can track, but even before that, we need to define what we want to achieve with the tire. So what do we want to achieve with the tire? We want to maximize grip and we want to have consistent grip, because it makes no sense for you to have ideal grip in one lap, then you overheat your tires and you have no grip whatsoever. So we're trying to optimize grip and have a consistent tire. How can we quantify that? There are a few different ways. The first and most practical way is looking at driver feedback. So you as a driver, you should have a very good understanding of tire grip, tire performance, car balance. It's not only about finding the grip, but it's about finding a balanced grip between front axle and rear axle. So us as tire performance engineers, we're speaking a lot with the driver, taking notes of what happened, and tracking the conditions. Because if the driver is giving me feedback when the air and track temperature are 10 degrees C, it's very different from when the track is at 50 degrees C and then the air is at 30 degrees C. So I keep track of driver feedback and in what conditions that feedback was valid. So the driver is telling me, okay, the tire took me a long time to warm up. I had only very good grip after 3 laps. Now I'm thinking, okay, what can I change in the setup or in the driving style to make that warm up quicker? Then the driver tells me the grip was not that good when we stabilized. Okay, maybe the grip that I'm thinking, maybe the tire is not at the ideal operating window. Is it too low? Is it too high? How do I go up and down? And then lastly, the driver is going to tell me, but look, actually the tire grip on the front was pretty good, but on the rear it was not. So in that specific outing, I was having a lot of oversteer. Now I can think, okay, what can I change in the vehicle balance to fix that? All right, so we defined first what we wanted, then how we get this information from the driver. There is something else we can do. We can look at the data and try to quantify with the data understeer, oversteer. We know that by looking at the steering profile, we can very well quantify or at least see understeer and oversteer. After that, we need to decide, okay, what do we do with all that information? What tire parameters can I keep track to understand if the tire was too cold or too hot? Then it all goes back to the good examples that you gave. So tire pressure, we should be measuring the cold pressure when we leave the pits and the hot pressure, because there is a whole art behind defining cold pressures to achieve the ideal hot pressure that you want. How do you know what's the ideal pressure that you want? Well, there are many factors. It's a lot about experience or running different hot targets or hot pressures and understanding which one gives you the best grip. But it's also a lot about driver feedback, because if you run very low pressures, your tires become unresponsive. They're lazy. Why? Because when you steer, they first need to deflect laterally, because now they're very soft before they grip and generate grip for you. So typically what I do with race cars, I keep lowering the pressure until the tire starts feeling lazy, unresponsive, and they don't give me the confidence or the support when I'm rolling that I want. And then I can find, okay, what's too low? And then if I keep increasing from there, I'm going to start losing grip, and then I can define ideal pressure. And we keep track of that with the pressure gauge. Now, speaking about temperature, what can we do to track that? Yes, one of them is the parameter. So actually, there is the ideal measurement and the non-ideal measurement. The non-ideal measurement would be with a laser gun or with an infrared gun, because you're only reading.
That's only measuring the surface.
Yes, you're only reading the highest surface or the most outside surface of the tire, which two things. Number one is not really what's going on at the track, because there is a lot of temperature inside of the rubber that is extremely important. Number two, when you finish your lap and you come back to the pits, it takes you a few seconds until you make the measurement, and the temperature is going down. More interesting, if you go to a different track with a different pit lane length, or if you're staying at the beginning of the pit lane or at the end of the pit lane, this is going to influence your reading. We see that it's not representative of what's going on at the track. The best one is to use a temperature probe where you have the needle and you can put the needle at a 45-degree angle. You go a few millimeters inside the tire. That one is very representative. It is a lot closer to the temperatures that the tire was seeing around the lap, and it doesn't cool down as quickly as the surface temperature. All right, so now we know how to track temperature. How do we determine what's the ideal temperature? Again, you have to run in a cold conditions, then in warm conditions, track everything, take notes, take feedbacks, look at the data, and then try to connect everything to determine, all right, so I had maximum grip when my temperature probe measurements were in this range. So whenever I'm in this other event, I need to either change my setup to increase or lower the temperature. You gave a very good example, for example, the toe. It's not the only one, but it's a good example. Or how can I drive differently to warm the tires more? I need to be more aggressive. I need to overdrive a little more. Or actually, I need to reduce the tire temperature. So I need to be a little bit more careful, a little bit less aggressive, overdrive a little less. And a strategy that we use in professional motorsports is whenever we have to lower the temperature or decrease the wear, there are specific corners where you take them slightly slower so that you do not overheat the tire, such as high speed corners that are putting a lot more sliding energy or energy in the tire. So that's how I would say that first we define what we want to achieve, then how do we track that, and then how we can optimize pressure and temperature for a given situation.
Okay. This, again, just like everything else we've talked about, is probably a podcast episode on its own, but I just want to dive a little bit deeper into it. So you mentioned essentially the laser measurement in the pits, and if not really going to give us much feedback because it's just measuring that outer surface, which is going to lose temperature very quickly as you're rolling down pit lane. You mentioned the tyre pyrometer that's going to measure the tread below the surface, so get a much more representative reading. You didn't mention the infrared tyre temperature measurement actually on the car, measuring the temperature in real time and the data analysis or data logging as the car's cornering. How useful is that? I mean, as I see it on face value, that would be the optimal because you're actually seeing what the tyre tread is doing in terms of temperature and temperature spread across it while the car is loaded up in the corner, which is what we want to know.
Yes, absolutely. Let's say that we go for this a little more expensive solution. It is the best that you can get. The only thing I have to warn you is that it's not easy to look at the data, but I can give you very good insights here of how to interpret this data. Because a couple of years ago, I was struggling myself to come up with useful metrics from the sensor because you get so much data, so many channels in different sections of the tire that you need to create a very systematic way in order to process the data. So in very high level series, then we can use temperature sensors. Actually, many of them it's banned. You cannot, at least you can only do in private testing. However, we developed very good methodology to do that. So what are the key metrics that I will try to extract from this data? This data is going to be changing. It's going to be all over the place. Each of the corners is going to have different temperatures. So I try to simplify that into a couple very useful metrics. One of them would be the following. As I mentioned, with temperature sensors reading the tire temperature around the lap, first thing, if it's on the front axle and the sensor is not following the tire as it steers, you have to be very careful with the results, right? On the rear, it's a little bit more straightforward. Though it is possible for you to create a mount that it rotates with the upright, and then you keep reading the inside shoulder, the center, and the outside shoulder. Typically, I like to have at least 3 readings, as I said, inside, middle, outside, but many times we have many more. My suggestion, simplify it. If you have 5, only pick the outside, middle, and inside. This is more than enough for us to analyze. Let's go back to the metrics. So the metrics that I try to look at are the following. Average temp, I don't look at each channel in all different conditions. I create metrics which are average channel of the 3 channels when cornering. Because a lot of people create this metric around the lap, but around the lap you have straight line where, let's say it's a rear wheel drive car, the front tire temperature does not matter. So let's think about lateral grip. Create this metric only look at it, for example, when you are at the apex. This is a very good way of simplifying it. So I create one metric which is average tire temperature when cornering. You can filter it only when you have high lateral accelerations. You create this metric. And the second metric, which I believe is very important, is the distribution. So inside shoulder minus outside shoulder, possibly when cornering as well. Why? Because it gives you a very good idea of what your dynamic camber is doing to your tire. If you have your inside shoulder very, very, very warm, even when cornering, compared to the outside shoulder, maybe you are running too much camber. You are too much on the inside shoulder. Your contact patch is focusing too much on the inside shoulder when you're cornering. While when you see a smaller gap of inside temperature and outside temperature when cornering, this means that you're making better use of your contact patch, meaning that you probably have appropriate camber. Just be careful. Let's not oversimplify because in straight line, you are driving on top of your inside shoulder. So it will naturally have a higher number even when you corner. So just be careful with how much you want to really have the same temperature inside shoulder or outside shoulder. But with experience, you start learning a little bit more of what is a good distribution for your car, or when you have good grip, what is a typical distribution that you see, or what is a typical average temperature that you see when cornering. So this would be the best strategy to analyze tire temperature.
Yeah, I've found that the onboard infrared tire temperature data is not maybe as straightforward to analyze, which you've just given us a nice reason for, or indication of, compared to what I thought it would be prior to fitting these sensors. And I absolutely agree with you that particularly if you're not a professional engineer, less is more when it comes to those data points. We've got Izzy Racing sensors on one of our cars, which will run up to 16 channels. And I mean, it's just generating more noise that you have to get through. So I actually did simplify that back to just 3 points across the tire. But again, on face value, you'd think, all right, well, this is going to be the perfect data. I can see exactly what's happening to the tire tread temperature through the corner. But the reality, of course, and I mean, it makes sense really when you think about it, just like you said, you're coming into the corner, the car has negative camber, so it's predominantly running on the inside edge of the tyres up to the braking zone. So obviously the inside of the tyre is going to start at a higher temperature as you initiate the corner and turn in and move through the corner. Then as the car rolls onto the outside or middle and the outside edge of the tyre, obviously those will start to build temperature. So then the next question for me was, all right, well, at what point through this corner now do I look at this data to get a sense of, is my camber and my tyre pressure correct? Because these are constantly moving targets. So thank you for your little tips there. I am absolutely going to steal those and apply them to my own car. One other element I just wanted to come back to as well, because obviously, as you mentioned, the infrared tyre temperature monitoring, it's an expensive step up. Tyre pyros that you'll use in the pits, these are much more accessible and relatively cheap. I think anyone even at club level should probably be considering purchasing one. But much the same, even when we're measuring the temperature below the tread, this is going to equalize quite quickly, particularly if the last corner before pit lane entrance is quite a long way down a straight, and then maybe, as you mentioned earlier, maybe you're down the end of pit lane, so there's quite a long period of time with the car rolling, mainly on the inside edge, before you can take those tyre temperature readings. So I think, again, most people who haven't done this before would think, all right, well, we're looking for the exact same tyre temperature number across the tread, inside edge, middle, and outside edge when we're using our pyrometer. I haven't found that to be the case, and generally I'm guessing here there isn't a black and white number like everything we've talked about, but I've sort of tried to start with maybe achieving a 10 to 15 degree spread across the tyre, with the inside hottest, the outside coldest by that margin, and then ideally the centre right in between those. Does that make sense in your experience, or am I off the mark there?
No, it does make sense. So as I was mentioning, this is such a complicated subject that we need to create a few rules to work with. Otherwise, we're stuck in what we're not doing anything. On the professional motorsports world, this is the range that we're typically expecting, a 10-degree split between inside shoulder and outside shoulder. If we're slightly outside that, it doesn't mean that we necessarily have an issue. If we're 30 degrees higher on the inside shoulder than outside shoulder, yes, then we should be worried. We're probably running way too much camber. So the range you gave is pretty good, and I would go with that as a starting point until we better understand our tires.
What I've also said as well is maybe start by baselining the car and getting yourself within that range. But like, let's say, for example, it's 15 degrees. Well, maybe make a change and see what the performance difference is. If it's a 10-degree spread, maybe go the other way. What's it like with a 20-degree spread? I'm basically just throwing numbers out there. But again, I mean, just basically mentioning there is no black and white rule of thumb that we have to stick to. It's a case of getting a baseline and then seeing, is it better with less? Is it better with more? Actually make some adjustments and try these things. Good advice there?
Yes, but at the same time, I'm going to go a little bit against what I do in professional motorsports when we're just at the track trying to optimize our own car. we should understand that there is only so much we can optimize with the information that we have. So it is important to know, okay, we should not completely disregard tires because they are the most important parameter, but there's only so much we can do with the information available. So if I get within this range, maybe I'm not going to overthink it, because if I change the camber to change this temperature spread, I'm not only changing the temperature, I'm changing the whole behavior of the car because of the new camber. So I'm changing multiple parameters at the same time. It's a little bit hard to identify what's really coming from the temperature change or the temperature split change or what's coming from the camber. So we just need to understand, where do we stop, where do we focus on the driving, where do we focus on the suspension, the aero, and so on. And it's also a lot about the level of racing to understand until what point you try to optimize it. But in professional motorsports, we're doing exactly what you're saying. We are tracking all of the runs and trying to find patterns between different temperature spreads, let's say.
One last thing, I don't want to do tires to death here, but one last thing, and this is just for my own personal knowledge here. We're often now seeing a professional level tire pressure monitoring systems incorporate infrared tire temperature on the inside of the tire, looking at the carcass temperature. And again, we run the Izzy Racing sensors on our own car. Like their external ones, you can have up to 16 points here. I'm wondering, this isn't a parameter I have put a lot of weight into so far, but I'm just wondering what you can tell us about the relevance of the carcass temperature internally, maybe what we can take from that, what we can use from that, and how that correlates to tread temperature.
Yeah, so actually, I'm very happy whenever I work with a race car with this type of sensor. So it's getting more and more common. First of all, the series allowing for that. But number two, it's a pretty expensive sensor. So it's taking a little bit of time until the team has enough sensors that match the number of rims that they have. In any case, it is a very useful sensor for professional motorsports because of a couple different reasons. It is a very robust reading, contrarily to the surface temperature. When we are reading the inside carcass temperature, it's changing a lot more slowly. So it gives a very good indication, okay, is the tire overall gaining more or less temperature with the sensor? Is this driving abusing more or less the tire? When we run lower pressures and the tire has a lot more deflection, is it increasing a lot the carcass temperature or not? So it's a very good way of comparing the overall tire temperature and the changes that we make to the car. But how do we use the number itself? We use it in a few different ways, particularly in endurance racing. Let's say that we go to 24 hours of Le Mans. In that case, the inside shoulder temperature is a very important parameter, because if this temperature is above a threshold that we define, this means that we are stressing too much the inside shoulder. We're putting too much energy on that inside shoulder. Not only that, you know that as the materials get warmer, they also get softer, and it's more likely that they're going to rupture at some point. So we use these sensors to understand how much we're stressing the tire and how likely we are to get a tire failure over a long race. So this is one of the main parameters that we use for that sensor. The second one is just because it gives a good idea of also what the surface is doing. Many series we cannot run outside surface temperatures, but we can run inside. Let me give you an example. If your carcass temperature is at 40 degrees, you should not expect that your surface is overheating. Well, for two reasons. If it was overheating in the first place, your carcass would be very warm as well. And the second thing, if you have a cold carcass, it's gonna drain a lot of this temperature from the surface. So if you go on a long corner, it's hard for you to overheat because a lot of this temperature is still going to the carcass because the carcass is cold. Now, on the other hand, if this carcass temperature was already at 120 degrees, even if you approach the corner with a very cold surface because it cooled down with the outside air, as soon as you attack the corner and any temperature that you gain, it's going to remain on the surface because the inside, okay, this is not the right physical term, but the inside tire is already saturated of temperature. So you cannot conduct this temperature from the surface to the carcass. So these are some of the ways that we're using to understand if we're overheating the tires or not, even if we don't have the outside tire temperatures. And before we move on from tire temperature, the only thing that I would add, which I think could be pretty good to our audience, on our YouTube channel of Optimum G, I recently published a 25-minute video explaining about everything, how tire temperature is affecting vehicle behavior and vehicle balance. So you understand how the temperature build up will give you an understeer car or an oversteering car. And I think it's a pretty useful video.
Okay, great. Well, again, we'll try and incorporate a link to that particular video. Obviously, through this whole conversation, which is now getting on towards 2 hours, we're dealing with some very complex topics, and we have tried to consolidate them down into bite-sized segments. So for every single thing that we've talked about, we could have probably gone on for an hour or so on each of those topics. So hopefully our audience can appreciate that. And on that note, I think it's probably time that we did move towards wrapping this conversation up so we don't go for another 2 hours. So, Bruno, first of the 3 questions we ask all of our guests, what's next in the future for you personally and also Optimum G?
Right. So for Optimum G, we actually have big plans. We hope to expand the company to tackle many different challenges that we see in the market, especially connecting vehicle dynamics with all the different systems of the car and a lot of the challenges that our customers face in this area. So we really want to continue to connect different tools, connect different solutions, and empower our customers to make better vehicle dynamics decisions and improve their vehicles. That's our mission. We're going to keep expanding on that front. We want to give more advanced vehicle dynamics or create more advanced vehicle dynamics tools, create more advanced data analysis tools, and we are headed in that direction. Besides that, for me personally, I will keep growing as the head of consulting. So I want to tackle more and more projects, coordinate all of them, and make sure we build things. So what I like to do is whenever we have a very challenging project at Optimum G, I'm the one tackling it at first, but then I'm bringing my team with me so that the next time they can tackle that. So I want to keep pushing more and more my consulting team towards more challenging projects.
Sounds great. And obviously your day-to-day sounds like it's always pretty exciting, never the same thing. So yeah, sounds like a position you'd probably never get bored with, which obviously is ideal. Next question for you, Bruno. Is there any advice you'd give to a younger version of yourself or maybe one of our listeners to help reach where you've got to in your career today faster or potentially maybe avoid some pitfalls that you've seen along the way?
Yes, I have a couple of important insights to share. The first one is you got to work a lot. I know this sounds obvious, but there are so many people that want to become race or performance engineers. So you really have to work a lot. You have to work more than all these other guys, let's say. And because of that, it needs to be something you love. Because it's one thing enjoying cars and being a car guy, and it is something else enjoying being a performance engineer or race engineer. It is a lot of stress. You work under a lot of pressure. You travel a lot. You don't sleep that much. So you need to be passionate about it so that you can get there. Second, and possibly one of the most important piece of advice is that if you're still a student, go for engineering in a school that has Formula SAE or Formula Student Project. It makes a huge difference because let's say that you're in school for 5 years, you're going to get 5 years of experience working on race cars even before you go and try to find a job. So that's a huge strength for those who do Formula Student. Besides that, I would also add that you should study a lot. At least for me personally, this is one of my strengths. When I go to the racetrack, I have the vehicle dynamics background to understand and solve complex problems. And whenever you're studying, try to apply that as you studied it. So let's say that you're studying tire performance. Find a project where you can apply that, being it creating a spreadsheet to track all of the parameters that we mentioned, being it going to the track with someone to help them with tire performance. Try to find a way to apply that so that you can really absorb that knowledge and you can make sense of it. And the last thing that I would mention, if I can add, is I also recommend that you grow as a person. So I'm always trying to study things like self-development, psychology, how to work as a team, how to work under pressure, how to be more efficient, because this plays a huge role in racing because you're always working as a team. And actually, this is another strength that you can have. If you work well, if you're able to handle stressful situations without exploding, or if you can still treat people nicely and find a logical solution, it's going to be a huge advantage in your career. So these are the insights that I would give to someone wanting to go to this direction of race and performance engineering.
Those are some amazing takeaways. I've said it before, and we've already mentioned the Formula student / Formula SAE element and how important that has been in so many of our guests. So, yeah, as I said at the start, very jealous that you had that opportunity that unfortunately here in New Zealand at my university, I didn't. I'd jump on that in an instant if I could have had my time again. The other element there, just the self-development, I think that's something that hasn't come up before, but is really, really important. So I appreciate that you did bring that up. As you mentioned, working in a race team is a stressful environment. You could be the best race engineer in the world, but if you do not work well under stress, or if you just cannot work and gel with the rest of the team, you're probably not going to end up having a long and great career in that industry. So yeah, it's a people sport. So being able to integrate with the rest of the team and work well with them is just as important as you being able to do your job at a high level, I think. All right, last question for today, Bruno. If people want to follow you and see what you're up to, how are they best to do so? Websites, social media accounts, what have you got for us?
Yeah, so in terms of Optimum G, I would say that our website will give you a very good idea of what our work is about. More than that, we have our YouTube channel where we publish content in vehicle dynamics, applied vehicle dynamics, being it tires, being it kinematics design. So a lot of what we covered here, we have specific videos on those topics. So it's Optimum G on YouTube. And also our LinkedIn is a pretty good page where we try to keep you updated with everything that goes on in the company. In terms of personal, I use a lot of Instagram to share my work. So I share a lot of the racetracks that I am at around the world, the consulting projects, how I organize my day, how I plan my week, and everything else behind my work. I try to share there. Besides that, I also have in my bio a lot of suggestions for resources to study vehicle dynamics, data analysis, performance engineering, and guess what? Also self-development, productivity, leadership, and communication. And my Instagram is bruno.finco. So you're going to get a lot of value from that as well. So that's pretty much it.
Amazing. Yeah. All right. Well, as usual, we'll put links to all of those accounts in the show notes to make it very easy for everyone to find. Look, Bruno, it's been an amazing chat. It has gone long, but it's also gone deep, and I appreciate your time there. I've certainly learned a lot during this chat, and hopefully our listeners have too. So again, thank you very much for your time today.
Thank you. I had a lot of fun, and I really appreciate the opportunity to be here chatting with you today.
If you enjoyed this episode of Tuned In with Bruno from Optimum G, we'd love it if you could drop a review on your chosen podcasting platform. These reviews really help us to grow our audience, and that in turn helps us to continue to get more high quality guests. To say thanks, each week we'll be picking a random reviewer and sending them out an HPA t-shirt free of charge anywhere in the world. This is also a great place to ask any questions you might have too, and I'll do my best to answer them if your review gets picked. So this week, a big shout out to Otto from the United Kingdom, who has said, "Such a great podcast. Topics are covered in good detail but broken down to respect audiences at all levels. My favourite episodes are Mike Kojima talking suspension, KW Suspension's Thomas, and Steve from Alcon. As somebody who's meddled with cars since being a toddler with my father, I learn something new with every episode." Thanks for the kind words there, Otto. We really love hearing that sort of feedback. And if you get in touch with your t-shirt size and shipping details, we'll get a fresh tee shipped straight out to you. All right, that concludes our interview. And before we sign off, I just wanted to mention for anyone who's been perhaps hiding under a rock and hasn't heard of High Performance Academy before, we are an online training school and we specialize in teaching a range of performance automotive topics, everything from engine tuning and engine building through to wiring, car suspension and wheel alignment, data analysis, and race driver education. Now remember, you've got that coupon code. You can use podcast75 at the checkout to get $75 off the purchase of your first course. You'll find our full course list at hpacademy.com/courses. Important to mention that when you purchase a course from us, that course is yours for life as well. It never expires. You can rewatch the course as many times as you like, whenever you like. The purchase of a course will also give you 3 months of access to our Gold membership. That gives you access to our private members only forum, which is the perfect place to get answers to your specific questions. You'll also get access to our regular weekly members webinars, which is where we touch on a particular topic in the performance automotive realm. We dive into that topic for about an hour. If you can watch live, you can ask questions and get answers in real time. If the time zones don't work for you, that's fine too. You're going to get access as a gold member to our previous webinar archive. We've got close to 300 hours of existing content in that archive. It is an absolute goldmine. So remember that coupon code podcast75. Check out our course list at hpacademy.com/courses.